physics eventually claims its due. In one instance, a refractory brick failure led to a localized 1450-degree hotspot, warping a 75-meter steel shell. This single failure caused a $45 million shutdown, proving that physics doesn't care about textbook assumptions when a massive machine destroys itself under its own weight. Behold the mega machine. This industrial cement rotary kiln is 75 meters long and 5.5 meters in diameter, spinning at 3 to 5 RPM to process 5,000 tons of material daily. The challenge? Managing extreme thermal entropy, specifically a 2,000-degree flame, without the machine melting itself. This is a brute force terraformer. Raw limestone enters the high end, while a jet engine of fire blasts from the low end. As the kiln spins, the rock tumbles, roasting into artificial lava or clinker, before dropping out the bottom. It is a constant battle against heat and gravity. We have spent a century fighting thermal bottlenecks. From manual 1880s kilns to the brutal mechanics of the 1900s and the reactive sensors of the 1990s, we have been brute-forcing production. Today, we enter the era of Industry 4.0, using AI-tethered digital twins to predict the fire, rather than just monitoring it. Conceptual models are often mathematically pure but disconnected from reality. On paper, fuel burns perfectly and materials flow seamlessly, but in the real world, chaos reigns. These 2D logic loops assume perfect balance, ignoring the physical reality of thermal variables. Caging the fire requires understanding the hidden load paths. From the refractory lining separating the 1450-degree heat from the steel shell, to the massive girth gear and riding rings, the kiln is a dynamic, rotating exoskeleton. It constantly fights gravity and thermal expansion to keep from snapping in half. Navier-Stokes and Stefan Boltzmann equations govern these processes. While the math is elegant, applying it to a chaotic mixture of rock, gas, and fire has historically been computationally impossible to solve in real time, leaving machines vulnerable to meltdowns. Traditional modeling is accurate but slow, often taking weeks. Physics-informed neural networks, or PINNs, change the game. By learning the laws of physics directly, these AI surrogate solvers bypass complex mesh discretization to predict thermal stress in seconds. We no longer guess. The machine is now permanently tethered to a real-time digital ghost. Through acoustic sensors, infrared scanners, and motor telemetry, the system feeds data into an ecosystem that understands the machine better than its operators, monitoring every vibration and thermal spike. Old PID loops react only after the fire has burned the system. Modern reinforcement learning is predictive. By simulating 1,000 future states continuously, the system preemptively adjusts fuel and rotation, engaging failsafes before a human operator could even register an error. The digital twin may be flawless, but the physical shop floor is not. Deflection, ovality, and imperfect mass mean the system is constantly fighting its own geometry. Gravity, rotation, and expansion create dynamic stresses that require constant, complex management. When we introduce variables like burning shredded tires, we create unmodeled entropy. AI is not magic. When the system chokes on unexpected chemical changes, blunt physical redundancies, like air cannons and hydraulic thrust rollers, take over to maintain integrity. AI does more than monitor. It redesigns. By running millions of evolutionary simulations, it creates organic geometries for internal components that far exceed human engineering capabilities, resulting in massive gains in thermodynamic efficiency and reduced aerodynamic drag. This is about more than making cement. Rotary kilns are foundational terraforming engines. By binding these analog beasts to AI, we are scaling our ability to process reality at the atomic level, transitioning from carbon-heavy methods to precision molecular control. The $45 million meltdown is a relic of the past. Entropy will always exist, and machines will always try to fail. But through the synthesis of blunt engineering and AI, we can cage that entropy, manage the chaos, and safely build our world.